Okay, so here we are, speed of a wave in the wave equation. Getting to the end here of all this frequency, amplitude, and we're going to tie it all together here, hopefully today. A wave, in review, is a disturbance that moves along a medium from one end to another. The particles vibrate and they move. Now, the speed of an object is how fast an object moves, and it's distance divided by time. You probably recall that way back in August when we talked about it. Now, one behavior that waves undergo in the end of a medium is something called reflection. So the wave will bounce off and bounce back. Now, we haven't talked about reflection, and we'll get into boundary behavior soon enough. But it'll reflect, and when it undergoes reflection, it remains within the medium and merely reverses its direction of travel. Okay, so distance then will have to be looked at a little different way. Reflection is commonly seen with sound waves with echoes. So when you yell, the sound waves leave, and the compressions and refractions, and they hit the surface, and then they bounce back to you. Okay, so when we talk about distance traveled with waves, especially those that reflect, remember this. Even though it's 170 to the end, it's 170 going back. So total distance traveled is 340 meters, not 170, even though it's 170 to the place. We don't hear it till it travels back. So, wave speed. Frequency does not affect wave speed. Wavelength does not affect wave speed. Amplitude does not affect wave speed. Wave speed is only affected by the medium it travels in. And that's a very important point, and you cannot forget that, because you will be asked questions about that constantly. The medium determines speed of the wave. Things, we talk about gases, we talk about liquids, we talk about solids. That will determine the properties, or the speed of the wave, not direction, distance, all of that. Now, we do have an equation for speed because we got to have a number. And it's wavelength divided by period, but more commonly we see it like this. Wavelength times frequency. You remember, frequency is just 1 over period, so essentially it's the same equation, right? Just different terminology. But speed, wavelength times frequency, or wavelength divided by period, either one works. But that's how we find wave speed. So let's talk about some questions here that could come up, and just to see if we are all on the same page here. All right. So we have, as the wavelength of a wave in a uniform medium increases, all right, its speed will do what? It'll get tricked. All right. As the wavelength increases, its speed will stay the same because the medium doesn't change. Okay. The wavelength may increase, but then the frequency will decrease. So it will balance out, and that will make sure that we have something common. So it has to change mediums for the speed to change. So as the wavelength of a wave in a uniform medium increases, its frequency will do what? Now this one has an answer. The frequency will decrease because the speed stays the same. So the speed of a wave depends on what? The properties of the medium through which it travels? You bet. The wavelength? No. And the frequency? No. It's the properties of the medium. That's what it depends upon. Okay? Changing wavelength and changes frequency, or vice versa, which doesn't change the speed. Don't forget that point. Okay, ocean waves travel the distance of water surface during a storm. Coast Guard Weather Station observes that there's a vertical distance from high point to low point of 4.6 meters. All right, so high point to low point of 4.6 meters. And a horizontal distance of 8.6 meters. Between adjacent crests. The waves splash into the station every 6.2 seconds. Determine the frequency and the speed of these waves, okay? So here's what we got. We have a vertical distance from high point to low point of the waves. Let me draw some waves. From here to here, the vertical distance, 4.6 meters, all right? Horizontal distance between adjacent crests, so from crest to crest, is 8.6 meters. The waves splash into the station once every 6.2 seconds. So every 6.2 seconds we have a wave cycle. So our period is 6.2 seconds. What's the frequency and speed? Frequency, 1 over period. So 1 over 6.2. And I get a frequency of 0.161 hertz. So that's my frequency. If I want to find my speed, I take frequency times wavelength. Frequency, as we just discovered, is 0.161, and our wavelength here to here, crest to crest, not this vertical, it's horizontal, 8.6 meters. So I take 0.161 times 8.6, and I get a nice, easy 1.4 meters per second. Okay, we got two boats anchored 4 meters apart. They bob up and down, so they're going with the waves, returning to the same position every 3 seconds. When one is up, the other is down. There are never any wave crests between the boats. Calculate the speed of the waves. So when one is up, one is down, and they're 4 meters apart. Okay, this is a half a wavelength, right? As we talked about with crest and trough on a previous example. So you got to multiply it by 2 to find the full wavelength, which is 8 meters. Okay, speed is wavelength times frequency. Sorry, wavelength times frequency. Okay, not velocity times frequency. Wavelength times frequency. My wavelength is 8 meters. My frequency is 1 over my period. So now as I try to find my period here, okay, I know that they return to the same up position every 3 seconds. So every cycle's 3 seconds. So my period's 3 seconds. So my frequency is 1 over that. So 8 times 1/3 is 8/3. Let's put this in a nice decimal. 2.67 meters per second. Wavelength times frequency, or wavelength times 1 over period, or wavelength divided by period, however you want to say it. 2.67 meters per second.